welcome back to lecture 13 on financial mathematics for actuaries. Today we are going to solve the difficult problem, that is unknown interest rate I while paying the loans. Okay. So the challenge here is whatever we were learned, the algebra that we use, the log function and all other things may fail in this particular setup. So what we will do is we will approach this problem methodically using three methods. That's what today's roadmap will say. The first one is the analytic method, which will be helpful for solving simple cases. Wherever this analytic method will fail to work, we have a method of linear interpolation, and that is basically the exam method which you will follow. But this had some drawback, it may not give you the accurate results. So what we will do, we will also discuss a method 3, which is the calculator iteration, and that's the practitioner's method. So with all these three methods, you will be equipped to find a good estimate of interest rate I. Okay. So what is the reference mapping for today's lecture? It's sections 2.2.5 and 2.4.1 of Braverman and section 4.1 of Chan and Say. Let us dive deeper and understand why finding this I is so hard. Let us look at the simplest case where I have some money and I know the present value and I know the future value, I know the period. So 100 into 1 plus I raised to 5 is equal to 150. No brainers here, you can easily find I by reverse engineering. That is, you just take those 100 to the other side, you will get 1.5 on the right hand side, 1 plus I raised to 5 is this. Okay, then you just take raised to 1 by 5 of that particular right hand side, and then 1 plus I is equal to 1.5 raised to 1 by 5, which is 0.2, then subtract 1 from that to get the I. No brainers here. However, when typically in the case of loan payments, you have to do multiple payments, and these multiple payments will make the matters worse. For example, now you look at the payment, the present value is 100 and then you are actually paying 10, 20 and 100 at first, second and third time point. So present value of that 110V, 20V square and 100V cube. Solving this cubic equation is not possible for a simple high school using the simple high school formula. It will be a difficult task. Okay, so we have to deal with it in a different way. But sometimes we may get lucky, we may not have to process the three payments, but the solution can be given by a quadratic formulation. Let us look at one question which is here. You are basically in today's class, the problem is finding effective interest rate I. So the problem says you pay 100 at t equal to 1, pay 100 at t equal to 2 and the loan that you are getting is 180. So this is the basic problem and I have to write the equation of value because the loan I am getting is 180, 180 is the present value equal to 100 first time period 100 times V, second time period 100 times V square. Okay, can I solve this problem? The answer is yes, I can. I will rewrite this in the standard form ax square plus bx plus c equal to 0, and now I have that formula which is the discriminant rule, b square minus 4ac greater than 0 less than 0. I hope all of you are familiar with that formula, and then if I apply that formula, then I simply get the value of v. So you can if you want, I can simply show this is nothing but a x square plus bx plus c equal to 0. So my a is equal to 5, b is equal to 5 and C is equal to minus 9. That's what I have to remember, and then I will simply plug into this formula. I know all of you are aware of this formula. Just for the sake of clarity, I am writing minus B plus or minus square root of B square minus 4 times AC upon 2A will be my V. Okay, so I will just go do to and fro. A is 5, B is 5, C is 9. A equal to B equal to 5, C is minus 9, right. So just plug in these values and see you are getting this formula. As usual, the negative interest rate is ruled out because it's not a valid number, right. So I will just focus only on the positive part of this number. So you do the calculation, the positive root, there is only one root which is 0.931, and this is a present value. Do I know how to calculate interest rate? Yes, V is 1 upon 1 plus I. So I know how to calculate the interest rate by just reverting that formula. 1 upon 1 plus I, we will get 1 by V is 1 plus I. So 1 by V minus 1 will give me the interest rate, and the interest rate will become 7.41. So this is very simple calculation. In this case, the method worked well. However, we have already shown an example where I don't have any easy way to calculate that formula, right. So how will I handle that? For that case, we are giving you a method of linear interpolation. Here, the idea is very simple. I don't know the exact value, so I will estimate the interest rate. Let us say I estimated lower interest rate. Then what will happen? I have one fixed loan amount in my mind, that is my target, and if I want to hit the target and if I estimate lower interest rate, then the present value of that particular interest rate will be somewhat higher than the target, right. And if I estimate the higher interest rate, because I am reversing back in time, the present value of high will be smaller than this particular target. That means I am trapping my target within two pivotal points, present value high and present value low. Okay, so this is the idea, and then I can use our linear interpolation technique. That means if I have some curve like this, and I don't know what is a value. So suppose somewhere here there is a target, right. I don't know what is the value at this point because this curve is invisible for me. What I will do is I will do the best estimate by drawing this line, and by drawing this line the estimate will somehow become somewhere close to this, correct. So that is the idea that we are going to follow. Okay, so the first step is you first guess the interest rate, you will get the present value. Because you have guessed the lower interest rate, the present value should be above the target, and then you guess the higher interest rate. Because you have guessed the higher interest rate, present value should be below the target, and that is how you will trap this present value into two regimes where you know the interest rates. And then what you will do, as I mentioned, you will assume that there is a straight line between these 2 points. Once you do that, then it's a matter of finding the slope and doing appropriate calculation, and that thing will be given by this kind of approximation. So for example, if your target is 100, your present value high will be 97.54, present value low will be 104.13, and remember that this graph is actually plotted over interest rate on the x axis, where interest rate and present value is given, and therefore it is of this form. Now when you hit the target, which is 100, you will get the interest rate of somewhere here. Remember, there is a gap in this approximation, or there is an error. Okay, so that you should always remember. This is how we will visualize the interpolation graph, and how to get rid of it is our next strategy. So before that, let us compute what will be the interest rate. For that, as I mentioned, it's a simple linear interpolation. You have present value low, which will be higher, minus the target, upon present value low minus present value high, which is multiplied by IH minus IL and I minus IL. So let me put why these ratios have come. So it's I minus IL upon IH minus IL. This thing should be approximately equal to present value of low minus the target that you have given upon present value of low minus present value high. Right. So this relation should be satisfied because I have to get into that triangle, right. So this is the relation that we have to satisfy, and that determines the slope of my line, correct. So this is like stating the equation of line, where I am determining the slope using these values and I am looking at this, okay. So that's all. And then your strategy is naturally clear. You will pick IL and IH close to each other. The closer they are, the more accurate is your answer, because the more drift from that curve is secured. Okay. So let us look at one example of the and see how this interpolation setup works. So here is an example where we have an investor who pays 100 at t equal to 0 and then receives 60 at t equal to 1, receives 60 at t equal to 2, and then we want to calculate the interest rate I that makes the present value of inflows equal to the outflow. That means 100 equal to 60 times V plus 60 times V square. Okay. Now I have to calculate the interest rate, right? So, so we have to guess something. So what will be the natural guess? Let us do a guess one which will somewhat sensible. It's 10%, right. So because $20 are increasing in 2 time points. Okay. So this is my guess of 10%. So what will that do? It will actually, if you look at this V, which is 1 plus I inverse 1.1 raised to minus 1 and 1.1 raised to minus 2, it will give me 104.13, which is our present value high, correct. So it's a 10% interest rate. What will happen if I increase the rate? I can take the guess of 20%, but 20% is too far. So let me be moderate. I can get a rate of 15% and see if I am going below 100 or not. Okay, so I have taken a rate of 15%, again did the same calculation and got 97.54, which is very good for me. So it's low and that is high, but I am deviating significantly from 100. Okay, so one is roughly close to 105, another one is roughly close to 97. Okay, so the answer I can guess is between 10 and 15. So I will plot a straight line between these two. And how will I do that? Using my interpolation formula. Let us list all the variables that are there. IL is 0.10, IH is 0.15, PVL is 104.13, PVH is 97.54, and then the baseline rate, which is 0.1, is given here. 104.3 minus 100 upon 104 minus 97 equal to 0.15 minus 0.10. This will simply give you an interest rate of 13.13%. How close it is? Remember that interpolation formula? My rate was varying between 10 and 15%, and if I draw a straight line crossing this, even though this is a target, this was the gap, right? Okay, so there may be some error that I have introduced, correct? So how will I understand that error? So this is my guess, this is my well estimated guess. I have 15%, I can reduce it, I can do another iteration. However, there is a simple trick, and why this approximation fails is what we have to understand. As I have shown you in the graph, this curve of present value is very convex. It's curved like a smile. Our straight line always cuts above this curve. At the target value of $100, the straight line corresponds to slightly higher interest rate than the true curve does. Okay. So I will give you an idea of how to do it on a calculator using BA2 plus calculator, and it is more efficient. It's an internal rate of return functionality of BA2 plus calculator. So what you do, you use your calculator, press the cash flow key, CF key, then enter the cash flow 0 to be minus 100. This is my outflow. Okay. After doing that, immediately enter C01 equal to 60, and how many inflows are there? There are 2 inflows. So F01 equal to 2. After doing that, immediately you press IRR, which is internal rate of return, and press compute. It will give you the exact answer, which is 13.06. This validates what we have got from our interpolation thing. There is a clear cut identification of the true value, which is 13.06 through internal rate of return, and the linear interpolation, which is 13.3. So this particular thing is actually a calculator iteration. Now, is the equation that if the equation you are looking at, will it always have a single solution? The answer is no, there can be multiple solutions. So we will give you one test case to demonstrate that, but why we are saying that will be given by this rule, which is Descartes' rule of signs. This is famous for polynomials. The number of positive real roots is at most the number of sign changes in the cash flow stream. Okay, so this is Descartes' rule of signs. The number of positive real roots is at most the number of sign changes in the cash flow stream. This is very important. For example, if you look at these two things, where the normal loan, you have one cash flow which is outflow, and then all others are inflows. So in such cases, there is only one sign change, so you will get unique interest rate. However, if you are looking at the complex projects where there are two negative signs or two sign changes, okay, negative, then some money has come, and then again the money has outflown. If such situations are there, there can be potential two roots. So the multiple root trap is alive there, and in such cases there is no easy escape, and therefore we will give one example, which is the example of mine closure, where you are digging a mine, the outflow is, the payment is due, so outflow is $100. You earn the revenue by whatever you received in the mine, which is 230, and then you have to pay the cleanup cost, which is again a negative sign, and in such cases your equation of value will be something like this. And now let us look at the interest rate, which is 10%. So V effectively is 1 upon 1.1, and you put all these values into this, you get the equation of value satisfied. So I is equal to 10%. Is this the only answer? You look at I is equal to 20%. Again, all the equation of value is satisfied, and there are two solutions, right? One, both 10% and 20% will have mathematically correct yields, right? So we have understood that if there are two sign changes, you need to be aware. governed by Descartes' rule of sign, right? And how to resolve that we will see sometime later, but this is the trap that you should be aware of. Okay, so we have learnt a lot in this lecture as well. Therefore, let us summarize this lecture. First, we have seen that algebra works only for single payment or quadratics. In real life, there are the situation is much more complex than these n is equal to 2. Okay, so we need a robust manual methods. So first is bracket and guess, and once we have guessed, you will use the linear interpolation for estimating the value, right? But the problem with linear interpolation is it slightly overestimates due to convexity, and in such cases what you will do, you will use this IRR, the fastest method, which will use the cash flow worksheet and can easily compute the correct interest rate. Okay. However, the uniqueness of this solution is guaranteed only if the signs change only once. Okay. So that is the understanding that we have developed up to lecture 13. Now we know how to compute unknown payments, how to compute unknown I, how to compute unknown time. What matters is which I, which is so we will answer this question in the next lecture. This I that we have figured out, which I is this? Is it a time weighted I? We have weighted it with time, or we have a dollar weighted rate. Which does it matter? So typically this comes as mutual funds returns and the investors return. So we will pose that problem in the next class, and we will show how both are correct, but they are using different I's, and for you which I will matter, time weighted or dollar weighted. We will answer that query in the next class. See you in the next class. Thank you.